So let's get started on the first one. We're kind of recapping transporting things across cell membranes. Cells are the smallest functional unit, and being the cell is the smallest functional unit, that means it has to function. And in order for the cell to function, it needs to control what is inside the cell from what is outside. Why? Because the cell needs to be able to control its environment to do its job properly. It would be like taking inventory, and that's your job. And your job is to take inventory of what is in the store. But if people keep selling things and stuff's coming in and out of the store and new stuff's arriving and new stuff's being sold and you have no control over it, it's really hard to take inventory. And so it's essentially the most important thing for cells to control what is inside and what is kept outside. And membranes do that. So membranes separate the intracellular fluid from the extracellular fluid. So that's intra meaning inside, from the extra meaning outside cell. And the fluid, really, it's what's inside that fluid. And cell membranes are allowing for exchange of the material between intracellular and extracellular fluid. And it's important not just for obtaining nutrients and oxygen, right? Because cells need to get O2 and get rid of CO2, but needs to get new nutrients for, yeah, you guessed it, cellular respiration. Also, though, we need sodium and potassium and all the ions, right? We need all this. And then the cell needs to get rid of its waste products, take the garbage out. And so cells are said to be selectively permeable. Now, if something is permeable, it means anything is allowed to pass through. But cells are selective, meaning cell membranes decide or restrict what can come into the cell or leave cell. And so this is a really important function of cell membranes. Cell membranes are selectively permeable. They allow the transport of some substances, but not others. They are not freely permeable. And what do cell membranes select? Well, nonpolar molecules, such as gases, fatty acids, steroid hormones, they are freely permeable. But ions and polar molecules require some type of transport to cross cell membrane. Whoops, let's cross cell membrane. And we talked about like glucose. Glucose requires a GLUT4 protein channel to be embedded in the membrane. And so you can have a cell, and the cell, this is inside, and all of a sudden a bunch of glucose shows up in the blood and it goes way up, right? So the concentration goes way up. Insulin gets released, and insulin's going to bind to a receptor on the cell membrane. And so, whoops, oh, I hate when that happens. And so insulin binding to this receptor is going to cause a second messenger system in the cell, which we covered a little bit. And that second messenger system is going to take these GLUT4 channels that are just hanging out inside the cell, and it's going to insert these GLUT4 channels. And that's really what insulin does, right? So it inserts these membrane channels, and they are specific for glucose. And now glucose can enter the cell. So it's going to leave the bloodstream and go into the cell. Why? Because it's a high concentration in the blood and a lower concentration inside the cell. So it's just going to be facilitated diffusion. That's what is occurring. So that's an example of facilitated diffusion. This happens for ions and all kinds of nonpolar molecules. And so if we look at table 1.4 or 4.1, because I'm apparently dyslexic, you see the intracellular fluid has a very high concentration of potassium, high, and a low extracellular concentration of potassium. But it's flipped. Very low intracellular sodium, very high extracellular sodium. Low magnesium inside, higher outside, low calcium. Calcium's a signaling molecule, and we use it for a lot of stuff. So it's actually used to help exocytose neurotransmitters and all kinds of stuff. So the cell really tightly controls these ions. Chloride, very high on the outside, very low. And in the nervous system, you'll see that this is chloride a lot of times is an inhibitory ion. You got bicarbonate, you got inorganic phosphate, amino acids, and you can see the different combinations, what's inside the cell and what's outside the cell. And so table 4.1 is explaining why membranes must be selectively permeable. We can't depend on people to stop eating sodium, right? We just love salt, tastes so good. Just keep eating salt and it'll just keep building up. And if the cell membrane wasn't permeable, or selectively permeable, all that salt would go straight into the cell and water would follow and that cell would blow up. So we do not want this to happen. And so cell membranes regulate what comes in and out through facilitated diffusion. And factors that affect direction of transport, well, there's passive transport, requires zero energy to be spent. What does that mean? No energy required. So no energy, downhill movement always goes from a high to a low. That's just the way. It's spontaneous, requires no energy, high to low. Active transport requires energy. That's why it's active. It requires energy to be spent, right? And so this is where we need that ATP needed for active transport. So 25% of your ATP needs are just for sodium, potassium, active transport pumps alone. Why? It's an uphill. We need to spend energy to go up that hill. You guys must notice if you're driving, say, up the Conejo grade, you're going to burn more gasoline than when you come down the Conejo grade. Why? Because going uphill requires the input of more energy. So that's active transport. The driving forces for diffusion and for ions moving and solutes moving is number one, the chemical forces. We call this the concentration gradient. What is the concentration on one side of the membrane? What is the concentration on the other side of the membrane? And the difference between the two is the concentration gradient. There, for ions, since there's a cation or anion, right? So there's a negative charge or a positive charge, there's going to be an electrical force. And so for ions, there's both an electrical and a chemical force, and we call that the electrochemical gradient. Still is passive, unless you're actively transporting against their force. And it's a high to a low electrical gradient, a little bit different. It's really pluses and minuses. So we're going to spend some time going over that. First, though, concentration gradients, again, it is the difference in the particle concentration between the inside and the outside. You can say chemical gradient, you can say concentration gradient for our purposes in physiology. It's how many molecules inside versus outside, how many, right? So from here, it does look like the concentration is higher on the inside than on the outside, and therefore the driving force is going to be going out because it's the difference between these two. It's going to move from the high towards the low. And so you can see it's a lower concentration in here. These, by the way, are concentration brackets. And so it's much higher out here. And so the chemical or concentration gradient is driving these molecules into the cell. That is, of course, if the cell membrane is permeable to that substance. So gradients push particles from higher to lower concentration areas, always going to go down the concentration gradient from a high to a low. Electrical driving forces depend on, and this is for ions, and it depends on the particle charge. So cations take on a positive charge, anions a negative. Why? Because more electron than protons, and this has more protons than electrons. And so if a membrane separates cations and anions across the cell membrane, it's called a membrane potential. It's potential energy. Why? Why is it potential energy? Because separating charges across the membrane means that there is potential energy since if the membrane opens to the ion, they will move towards each other. And really the key is movement. Those ions moving is essentially the electrical currents in your body. And so membrane potentials is the amount of current that can be generated if those ions are allowed to move. And so it's called potential voltage or energy because it's only turned into voltage or energy when the membrane allows ions to move across the membrane. That is to say, up until the membrane allows these ions to move, it's only potential to create a voltage or energy. So membrane potentials, that they are a force. They're caused by the unequal distribution of anions and cations across the cell membrane. There's a charge separation, which is the source of energy due to the membrane maintaining separation of charges. And the inside of neurons and many cells is a negative 70 millivolts. And what this negative means, there are more anions inside the cell to the tune of 70 millivolts more negative. That's what the negative denotes. So the magnitude of a membrane potential, right? So Vm is membrane potential, is equal to the strength of the force, is equal to potential energy. And I'll tell you right now, the bigger the difference in concentration gradients, like in cellular respiration, when we got to the electron transport chain and oxidative phosphorylation, the bigger the concentration gradient of protons across that inner mitochondrial membrane, the more energy, potential energy was there to form ATP. So you can form more ATP. The bigger the concentration gradient, the more potential energy, the more you can do with that energy. The bigger the magnitude of difference between anions and cations across the cell membrane, the bigger the magnitude of voltage. And so the bigger the difference across that cell membrane is going to mean how much voltage that cell can potentially have. It's in reference to intracellular fluid. It's more anions in the intracellular fluid. That's why we're saying it's negative 70, because we're talking about what's inside the cell, more negative inside the cell. So electrical driving forces, the principles are opposites attract. Cations and anions are attracted to one another. If you had a bunch of cations on one side, cations on the other side, they have no interest in moving across that cell membrane, but the opposites attract. And the direction of the electrical driving force is going to be determined by the polarity of the cell, meaning, is it more positive inside? Is it more negative? Well, we've been saying, it's a negative 70. That means cations want into the cell, right? Anions aren't going to come into the cell. There's already a bunch of negative anions inside, so more aren't going to come in. And then the charge on the particle, some cations have lost 2 electrons, and they have 2 more protons and electrons. So it's going to be double, say, what sodium, which only has 1. So that's the charge on the particle. That's just an example. We really don't factor that in much when on the things that we're going over for physio. So the magnitude, strength of the membrane potential, which is, how much difference in charges across the membrane, how much more negative than positive is it across the membrane? And then the amount of charge on the particle. Is it calcium with 2 more protons, or the sodium with 1 proton, or potassium with 1 proton? The electrical chemical driving force, that is the total force acting on particles. That is the sum of the chemical and electrical forces. So we are taking into effect the concentration gradient and the electrical gradient. So both of those together. Now, if the chemical and electrical forces are acting in the same direction, that's a huge driving force to go into the cell. So electrochemical forces can act in the same direction, but they can act in opposite directions. And I'm going to give you an example of that in a minute. But the absolute magnitude is the sum of both the chemical and electrical forces. And so let me give you an example. Membrane potentials is a separation of electrical charges that exist across the plasma membrane. And that membrane potential provides an electrical force that influences the movements across that membrane, and opposites attract. So if it's negative 70 millivolts, that means there's a whole bunch of anions, and it's negative inside. Now you have chloride out here. Does it have a big electrical gradient to go in? So this is a question. Does chloride have a big electrical gradient to go into the cell? And the answer would be no, because chloride's an anion. There's already a bunch of anions and doesn't have a big electrical gradient to go in. But the concentration gradient is really high for chloride outside the cell and really low for chloride inside the cell. So it does have a concentration gradient to go in. But one of those forces has to be bigger than the other, or chloride's not moving. And that's where we get into equilibrium. So again, to review, if the chemical and electrical forces are in opposite directions, like I showed you with chloride, this example, it's potassium, the electrochemical force is going to act in the direction of this stronger force because you are adding together the chemical gradient and the electrical gradient. And so the question, if a chemical gradient existed, under which conditions would a particle not be transported across the membrane, even if that membrane was open or permeable to the particle? And that would be if the electrical force is absolutely 100% equal and opposite to the chemical force. So it's showing you the example here. And let's look at this. The example is for potassium. Potassium's equilibrium potential, and that is equilibrium potential for potassium. That is this right here. The equilibrium potassium, or equilibrium potential for potassium, is negative 94 millivolts. Well, generally, the inside of a cell is negative 70 millivolts. So this is not the example of a normal cell. This is an example of the inside of the cell is negative 94 millivolts. And so the electrical driving force is completely canceled out at this point by the chemical driving force. They are equal and opposite. And so that is why potassium won't move, and it's at equilibrium potential. But again, normal cells are negative 70. So if this is a normal cell, and I erase this, and I say it's negative 70 millivolts, and potassium's allowed to move, which way is it going to go? Well, it's still going to leave because its electrical gradient is bigger than the chemical until it gets down to negative 94. That means negative 14 millivolts has to leave inside of cell to get it down to negative 94 millivolts, and then potassium stops moving because it's at its equilibrium. It's equal and opposite. So equilibrium potential, a membrane potential exists because electrical forces and chemical forces, for the most part, they're in opposite directions. The equilibrium potential is the concentration gradient for a given ion, though, can be opposite. And so this is the reality for potassium in a neuron. That is to say, there is a chemical driving force and there is an electrical driving force. And potassium will continue to leave the cell until inside of cell is negative 94 millivolts. So that is the electrical driving force to get down to negative 94 millivolts. Its concentration gradient is huge to go out of the cell. And so potassium has a driving force to leave cell, has an electro, that's supposed to be a C, chemical gradient to leave cell until cell is negative 94 millivolts, then no potassium moves. Why? It's an equilibrium. What is equilibrium? The chemical force is equal and opposite to the electrical force. And so that's what the equilibrium is. Next lecture, we're going to add on to that. Stay tuned.